Hello, this video is for section 5.2, Annuities, Future Value, and Sinking Funds. So we're getting out of the idea from compound interest where you just deposit one amount, it earns interest, then you finish with a final amount. Now we're involving making periodic payments, also known as annuity. This is first sentence here, a sequence of equal payments made each equal periods of time is called an annuity. And so, in other words, talk about future value of annuity means you're making periodic payments at whatever they may be, monthly, quarterly, semi-annual, earning interest, and then seeing how much we'll have at the end of the period, the end of the time. And we also will be looking at annuities if you were depositing a lump sum now and getting payments paid back to you from that annuity amount. So the first thing we're going to talk about is ordinary annuities. Ordinary annuities are when the payments are made at the end of each period. It will have a different name and a different calculation whenever we see payments at the beginning of each period. But for now, we're just starting with ordinary annuities where they are at the end of the pay period. Now we have what's called the future value of an ordinary annuity. So your PMT here is payment. Your interest rate, which is R divided by M, means like compounded. So for example, compounded 8% quarterly would be 0.08 divided by 4. And then we have a -1 up here in the numerator. Then we're dividing by that same interest rate down at the very bottom. Okay. It's the only time you wouldn't really be dividing by some M if M was 1, if it was annual. Then, so in other words, 0.08 annually would be just 0.08 because it'd be 0.08 divided by 1. Don't worry about this fancy notation over here. This is used a lot in more theoretical uses of interest or whatever. We don't need that. This is fine. And basically this whole S angle thing there, it's called S angle N, I believe, is just the stuff in the bracket right here. So, all right, let's try this out. And then I'm going to show you how to do this TM solver in the calculator, show you how to use the formula and show you how to use this. This problem, you would have had 6 total periods, interest is 8%, payments $1,500, and it's kind of weird in this application is that the number you're entering, you're supposed to put it in there as a negative. Although if you don't, I believe it should just give you the negative of what the right answer should be. It's not a big deal, but I may catch one of the notes where I forgot to do it, possibly. I corrected some other ones I saw that I didn't do it. But you enter negative and you put 0 for something you don't want, the present value. And so this means that 1,500 payments annual. These PY and CY are going to be the same number for our purposes. That's how many times a year. So 6. So it was 6 times, once a year, 6 years. So $1,500 deposited once a year for 6 years, earning 8%. Finished with a value of $11,003.89. In the calculator, for ordinary annuities, we choose end. The begin will be the other example we'll see later. Okay. So you have to set 0 in for stuff you're not using, in this case like the PV. But we'll do this in real time here in just a minute for another example. And certainly in the homework. Let's look at this example. It's out of the book there. So we have a rate of 1.11% interest monthly. We're contributing $950 a month. And it's 1.1% compounded monthly for 10 years. How much will we have at the end of the 10 years? So here it is. They've got the formula written out here, but I've just entered it as if I typed it into the calculator. So it's 950 times 1 plus 0.0111 divided by 12 raised to the 120. 120 comes from right here. It shows you 12 times a year for 10 years. 10 times 12 is 120. Then the minus 1 at the end, and then divided by the interest again, 0.0111 divided by 12. And that gives you a value of 120,508.87 rounded to cents, like they have right there. So here it is. It's 120 for the end, 1.11 for the interest. Like I said, I'll probably do one here in just a minute with a new example. Certainly in the homework I will. And one thing to note here is that when you enter the interest, if you're using this TVM solver, you don't change it to a decimal like you do in the formula. So in the formula, 1.11 would be written as 0.0111, not here. You put it exactly in the percentage, and the built-in program is taking care of the converting it to decimal. So we enter the payment as negative 950, and then got the future value of 120,508.87. Sinking funds. Sinking fund is a fund to set up to receive periodic payments. You can set up a lump sum and get payments from that. Also, you can look at sinking funds as being sort of like this last example where you're making payments where a company might be saving money up and, okay, we need to have X amount of dollars at a certain point in time to replace equipment or computers or whatever needs to be. So it's kind of like a savings fund, just periodic payments instead of a lump sum. Now, if they're made at the end of the period, that forms an ordinary annuity. All right, so this example, company is going to deposit $12,000 at the end of each quarter that earns 5.2% interest compounded quarterly. How much will be in the account of the sinking fund after 10 years? So they're going to know how much they're going to have to spend whatever they need to spend that on for the business. Now let's see if I copied this one to the calculator. It looks like I didn't since it was right here, but there's exactly how it would be entered in the calculator. So it'd be 12,000 times 1 plus 0.052 divided by 4 raised to the 40th, minus 1 all over 0.52 divided by 4. Now I'll go ahead and put this one, even though it's got the TVM solver down below, I'll do it for this one anyway. You come over here, it's under Apps, Finance, TVM solver. So I'm going to go back and look at the numbers. We had 40 total payments because it was quarterly, each 4 times a year, 10 years. 10 times 4 makes 40 payments. The interest is 5.2. So once again, we do not convert that to decimal. I'm going to zero out the present value. I don't want that. The payment, I'll make that as negative. I believe it was 12,000. And then I'm going to come down here and change that to 4. When you change the first one and you move the cursor, it changes both of them. Come down here, end of the period, make that say end. All right, then to make it do what you want to do, you come up here to the value you're looking for, which is the future value right there. You go alpha. Down here above the enter, there's a thing that says solve right there above the enter in green. So you go, the alpha brings up anything green on the calculator. So you go alpha, hit the enter, which brings up the solve, and then there's your future amount. 624,369.81. And there it is. That matches the formula right there. And there it is, what I just did right there. Okay, this one, now let's see if it lists the formula where yeah, it probably should have put this formula in here before this example, but that's okay, because we can just scroll right down and I'll show you. Suppose you're solving for the payment amount. In fact, I'll do that right now. Now, what they did is they left the formula alone here, worked out the inside, then divided by both sides, and by what was in the bracket, this number here, and then got the payment amount. But actually, you can do it using the formula right down here. We also can do it in the TVM solver. It's just an algebraic representation of what the original formula was. So when the payment comes over, that numerator moves down, and then the future value ends up there. So it's just basically an algebraic rearranging of the original formula. So I wouldn't go through and do it the way they're doing it here. And this is the way I entered it in the calculator right here. Let me show you. I'm entering it as if it was right down here. I kind of don't like the way they sort of have this FVI here. I would have put a dot between the FV and the I to make it look like it's two separate things multiplied together, because it almost looks like it could just be one thing, FVI. But it's not. It's FV times I. I would have used either a dot or I would have used parentheses if it was me, but that's okay. So you can see what I did right here. I took the future value of 200,000, multiplied it by 0.06 interest. And because this is annually, I didn't show the 0.06 divided by 1, like in the formula, neither did they. But it's because it's 0.06 divided by 1, same thing here and here. So it doesn't, 0.06 divided by 1, of course, is just 0.06. And we have 15 payments because it's once a year for 15 years. So they're using this money to replace a roof, or at least some of the money to replace the roof. Okay. And so you didn't have to divide by anything here. So in the TVM solver, 15 for N, 6%. This time you put in the future value, which is 200,000, 1 and 1 for annual, end, and then you go up to payment and you do the alpha solve that we did in the last one, and it's going to spit out the payment. Okay, that's a good example. This is what they did right here, which is fine, I guess. It's not a big deal. But they had they entered negative 200,000 here, they would have gotten payment of positive 8592. So that's not going to mess you up or anything really if you forget to put the negative there, because if you get a negative here, it's just going to be the opposite of the correct answer. So yeah, so it's not going to hurt anything. I try to remember to do it whenever possible, but here's one where they didn't do it. All right, so here's that. Anytime you're calculating the payment, we do it that way, or we do. So here's a checkpoint problem that I've done both in the TVM solver and using the formula just shown up there. So it's, let's see, Francisco needs 8,000 in 6 years to go on archaeological dig. Deposit equal payments at the end of each quarter, so he will have enough to go on the dig. Find the amount of each payment if the bank pays 12% interest compounded quarterly versus 8% compound interest quarterly. Okay. So naturally, if it's earning more interest, it's going to take, the payment will be smaller. Okay, so using the formula, you take the 8,000, you multiply by 12%, 0.12 divided by 4 because it's quarterly. Then on the bottom, you have 1 plus same interest rate, 0.12 divided by 4. You're raising that to the 24 because it's 4 times a year times 6 years. So that makes 24 total payments. And then minus 1 is always part of that formula. And you get 232.38. In the TVM solver, We have N is 24, interest rate's 12. Zero out the PV, we're not looking for that. And we put in 8,000 for the future value. Okay, here's one. See, okay, I forgot to do it. Some of them I do it, some of them I don't. It's not on purpose, but I did not even put the negative in there for the future value, just like that example they did. So it just makes it spit it out as a negative payment. So no harm. That's okay. It's kind of weird that it does that at all, but I don't know why. 4 times a year and the end, because this is an annuities. It tells you, if it just says ordinary annuity, that's good enough, or equal payments at the end of the period. If it says end of the period or annuities or ordinary annuity, both that means the same formula. We'll see how it's worded differently for the other situation when we reach it. So you choose end, and then the only difference between these two right here is just the interest has changed from 0.12 to 0.08. That's all. And still 24 periods, so interest now 8%. So you get $262.97 would be the required payment if the interest is 8%. All right. Okay, here we go. Here's a thing called annuities due. Annuities due means that the payment's at the beginning of each period. So the wording is either got to say it's annuity due, or if it just says the payments are at the beginning of each period. It's the same thing. We use this formula. Now, I didn't copy from the book or didn't go through really in the lecture the math of why these formulas turn out the way they do. It's not important for you to know either, but if you wanted to look out of curiosity, you could. It's a little complicated, but you don't need to worry about why the formula comes out the way it was. But you're actually subtracting a payment here because you have one payment that doesn't earn interest. So that's sort of, you back off one of the payments. Now using the formula, so there's the difference here. Your exponent here is n plus 1 now. It's not n. It's adding one more and then subtracting one payment off. So there's a difference. So the n plus 1 instead of n, and then you just subtract the amount of the payment right there at the end. You still have the payment multiplied in front. But if you want to look at that and how that's done in the book, go right ahead, but it's not necessary. Alrighty. So let's try this out. So here's an example I just took out of the book. Elena will make payments of $500 at the beginning of each quarter for 7 years. So there's your clue. Interest rate 1.08%, compounded quarterly. Find the future value of this annuity due. So it's using both phrases to make this annuity due. It's saying beginning of the period payments, and it's flat out just saying annuities due. So it's just reinforced it. But it did not have to say annuity due, because once it establishes the payments are at the beginning, that guarantees it is an annuity due. All right, so now I didn't put, okay, I guess I didn't put this one in the calculator. I did the next one. But let me sort of show you here. This is what I would have entered in the calculator. So now we want the future value. Go back to the formula. So the payment's 500 and 1.0027. And the exponent is 29 because it's 4 times a year for 7 years, which makes 28. And then you add 1 to that according to the formula. So it'd be right there. Be 28 plus 1 makes it 29. And then the interest is 1.08, which is 0.0108 divided by 4. That's where there it is right there. So it's showing you where the 0027 is coming from, because it's 0.0108 divided by 4. And then we get 14,561.66. Now this is very interesting how you do this in the TVM solver. You do not change the total number of payments. You don't add 1 to that. You put in, so N is 28, which means 4 times a year for 7 years. And you, oh, I forgot to mention down here, you see also at the end of this formula, you subtract off that one payment of 500. So the 500 is multiplied in front, then you subtract off that one payment right here. TVM solver, you don't subtract off a payment, you don't do anything. What makes it do the correct calculation, down here on the last line, you choose begin instead of end. When it's an ordinary annuity, you choose end. When it's the annuities due, you choose beginning, so you leave that at 28, your interest rate 1.08, put in the payment, which is 500, there's the future value, and it's 4 times a year. So there's the key. If you're using TVM solver, you do not change the N to 29. Well, N is actually still 28. Let me correct that. N is 28 in both of these. It's just the formula is N plus 1. That's what adds 1 to it. So it's not like it's a different N. N is still 28. All right. So I'll do this one, redo this one in the calculator. Might not do both of them. I'll just do the first one because it really isn't much change from the... Yeah, sometimes I remember to put the negative in there for the value. Sometimes I don't, but it's not hurting a thing. And $800 deposit at the beginning of 6 months for each 5 years. Find the final amount if it's 6% compounded semi-annually. So 6% semi-annually, 2 times a year, 5 years. That means there's 10 payments period. So I'm going to look at the formula first, then I'm going to do the TVM solver in real time. So you take the 800, you multiply it, and here's this big fraction, then 1 plus 0.06 divided by 2, you raise to the 11th because it's n plus 1, 10 plus 1. Minus 1, and then you divide by the interest rate, both places, 0.06 divided by 2. Then you subtract off the 800 at the end. And that gives you 94462365. Okay, I got the TVM solver already up, so I can just change the numbers here. That's 10. I believe that's 6. That's 0, negative 800 maybe. So I'll go ahead and make it negative this time. You'll see it won't make any difference. And semi-annually, I believe. Let me double check though. I think that's right. Yes. And here's the key. You go down here, change that to begin, but I still have to go back up here and highlight what I'm going to solve. So I got the payment in there's negative 800, which just means the future value will display as a positive number. But very important, you change that to begin. Now I go alpha, and I go solve. 944624, just like we got right here. Now the next one in the formula, you see there's no subtracting off 800 at the end. That's one difference, and the other difference is your exponent here in the formula is 10 and not 11. So you got a different exponent, and you don't have the minus payment at the end. There's your new values, 917110. And I'm not going to retype this in the calculator for this particular problem, because all you're doing is just changing this to end instead of beginning. And you go back up and do the alpha solve at the future value. So you can see this TVM solver shows what value you solved for. It puts that square block right there about whatever you're solving for. So isn't that delightful? So it's explaining what I was explaining earlier, that you don't put 29, you don't put the extra payment in the calculator like you do in the formula. That's what it's telling you here. All right, let's come down here. Payment for the future value of an annuity due. So it's a similar kind of idea. I'm not going to worry about showing you the algebra of how it's derived from that other formula, but it is. They basically factor, if you take that, I'll just tell you real quick. They sort of like factored a payment out of both those payment variables there, so you got a -1 and moved all that around, and okay, that's where the -1's coming from. So there it is. So just follow this if you're using a formula. Let's see, now they're talking about present value, so we're going to see if we have an example coming up. Might be like on the, is there one here? Let's see. Okay. Well, we may not even use that formula. We'll see. We may not, but it's there if we need it. So, and also it wouldn't be hard in the TVM solver if I had an example here to do. We jump down into present value. Okay. Now, present value of an annuity is if the amount must be deposited now to provide all payments for the term of an annuity. And this is also in the next section how we're going to handle loans and things like that, except the difference is you're borrowing the money versus using your own money. So let's say you had a nice little chunk of money, whatever, inheritance or lottery or something, and you wanted to pay yourself. Hey, I want to pay myself an extra, $2,000 a month for the next 20 years or whatever interest rate. You can figure out then how much money would you have to put up now to receive payments. Okay, we're going to start with ordinary annuities for this. So the present value equals payment, and a little different here. It's 1, so the 1 goes in front, 1 minus 1 plus I, and you see the exponent's negative n. That's not a typo. It will be negative n, and then divided by I, in which everything else, I is R over M, and N is the total number of compounding periods. So nothing changes there. So let's try this out, and then obviously we'll see. So this is kind of what I was just saying. They got a nice little caution for us there to not to confuse it with the other formula with the different numerators. Okay. So this one is, we'll do the next one, the calculator, but this one is, I don't know where I got this from. Must be for some example I didn't copy or whatever the case being, but I can sort of tell you what happened here. There were 84 total payments. So you see these two numbers are 12, so that means it was for 7 years. 12 payments a year for 7 years. And we want $2,000 a month at 4.7% interest. How much would we have to have on hand right now? What kind of deposit that we would have to make to guarantee that payment? Okay, so we choose end. So now this one, now we're not using future value, we're using PV for present value. So you always zero out whatever you're not using there. Okay, this time they did put the negative in there, but you could have done it with positive 2,000, just would have been the PV, would have been negative. So then you go up and select the PV and you do the alpha solve. So same kind of idea. You're just solving for PV now instead of FV. All right. So let's try this one out. Insurance company offers to pay Jayla ordinary annuity of $3,000 per quarter for 5 years, or the present value of the annuity now. If the interest rate is 6%, find the present value. Okay. So it'll be 3,000 times 1 minus, so 6% quarterly, 0.06, and just say ordinary annuity, 0.06 divided by 4, and then the bottom be 0.06 divided by 4. So we get 51505.92. And then I'll just do this one in real time, the calculator here. 20 payments. 6%, I think. Well, better look. 6% quarterly. So this, I say I need to zero out the future value here because we're not using that. And the payment is 2,000, 3,000. So I'll go ahead and leave the negative there. Negative 3,000. And I need to come down here though and change, be careful, sometimes I forget to do that too. But change this back to end, this ordinary annuity, so that needs to be end. Come up here and highlight the PV. We go alpha solve. There it is, 510.592. So basically they're offering to pay that now, or how much would you get if you were actually getting the payments? So it's factoring in the earning of interest and all that. So I'll just try to do this in my head real quick, but 3,000 per quarter be 12,000 a year. So you ultimately would receive 60,000 in actual payments, but the amount is lower, assuming it can earn interest or whatever. So yeah, so that's the difference. So if you maybe didn't trust yourself not to blow it all, getting the annuity might be the way to go. So, but mathematically they're equivalent in that sense. All right. All right, so what do we got here? Oh, that's the last page. I thought I had, the payment, the payment formula is just where you move, you're basically dividing both sides. So basically the payment, sort of like the future value, the payment will equal the present value times the reciprocal of this fraction. You just flip it over. I thought I had that copied in there or pasted in here. Okay, I paused the video here where I could do a little cut and paste job on that other formula to make it look like what it looks like right here. Like I said, I just moved the terms around and made them look like what they're supposed to look like. So there it is. So this one, 80,000, 4.8% interest compounded monthly. And you want to use up the money, but pay it out monthly withdrawals for 15 years. If interest rate's 4.8%, how much would you get each month? All right. So it'd be 80,000 according to this formula here. So 4.8 monthly. So it'd be 80,000 times 0.048 divided by 12 over 1 minus 1 plus 0.048 divided by 12 raised to the negative 180. Negative 180 would be from 15 years times 12 times a year. 12 times 15 would be 180. So 624433 a month for 15 years. So in the formula, we choose N because we're doing just regular, normal, ordinary annuities. Now this one you can assume it's an ordinary annuity, even though it doesn't say that, but it is. We didn't really do anything for annuities due in this like we did for the future value, so we're not going to worry about that for present value. So I had to zero out the future value. Whatever we're not using, you got to zero out. So if you do a new problem where you've done a future value and then you're switching to a present value, just zero out whatever you're not using. Put in the negative 80,000 for the present value. Came down here, picked the payment, and then did the alpha solve, and it gave us 62433. So that takes care of the lecture notes. So now let's move on and look at some homework examples. All right, here we are in the 5.2 homework. So I'm going to pick a few of these. Let's see what we got here. Now, sinking fund, payments at the end of each period, so it's pretty much a normal ordinary annuity. All right, so we don't have to worry about the annuity due for this one. That's kind of weird with this fractional number of years, but that's okay. If you're not sure, you can go 4 times. I guess, well, I wonder if it'll like 3 3/4 or not. Let's see how it handles. No. But that needs to be, I know the answer to this needs to be 15. Okay, it likes parentheses there. Okay. Yeah, basically 3 3/4, so 3/4 of a year would be 3 payments. And then 3 times 4 would be 12, so it's 15 total payments. That's a little weird, but that's important if we're using a formula in the calculator, which I will right now. Then I'll do the TVM. So it's going to be, all right, amount of each payment. Okay, so we're trying to reach 54,000. So we're going to use the version of the formula that does this, where it takes this amount and it multiplies by the interest will be on top. Oh, I don't want that. So it's interest 7.5% compounded quarterly. So I'll do a fraction here. 0.075 divided by 4. I'll do parentheses 1 plus, do another fraction, 0.075 divided by 4. Oh, I didn't, there we go. And that's, we already talked about that, it's 15. All right, this should be it. 315088. Yeah, it did say nearest cent. I have seen problems that you have to be careful in the homework. Not going to be an issue in the test where you're looking at the answers. That's a lot easier, but it may say nearest dollar. I've seen that every once in a while, but so let's put this in the TVM solver. We know now we know the answers, right? So apps and finance TVM solver. So we're looking for a future value problem. We're actually solving for the payment, but we just know that's going to be 0. This is 54,000. And it's quarterly, so the 4 is already. So this was 15 payments. We already established that. Interest rate was 0.0. 7.5. I said 0.0, but I don't have to enter it as 0.0 here. I guess I could if I want to, I'll just put the negative symbol in there. So 4 times a year is correct. End is correct because it's ordinary annuity. Oh no, I'm sorry, that's not right. But yeah, it is. Try to talk myself. And then solve for the payment. So I'll go alpha, solve. There it is. So 315088. There we go. So for a sinking fund, you can solve for either payment or the amount you're going to have at the end. I think generally sinking fund applies where it's just the payment, but it, still kind of the same idea. You're either trying to raise an amount at the end or you're paying off an amount. Either way, should be clearly worded, to which 4 I looked kind of interesting because no, it wasn't this one. No, 4 is the same as 3. Okay, it's 5. 5 is annuities due. It says right there, annuity due at the top. So and quarterly, 11 years. This time I'll do the TVM solver first, and then I can do the formula. And so 15,000, 11 years, quarterly. That makes 11 times 4 will be 44. Okay, we already got quarterly. Let me go ahead and I'll jump ahead here and I'll go ahead and highlight the begin right here. So it's annuities due, so we use begin. And let's see. $15,000 is the future value. Okay, the PV is still 0. And now I can go alpha solve. So I like 21832. Oh, thought I was. All right, let's see where I went wrong here. Payments are at the beginning. 15,000. Oh, the interest rate. I didn't put in the new interest rate. Okay. 4.1. That's the only thing I didn't change from the last one. So let's go back here and highlight this now. Let's try 268.75. Okay. All right, well, that's good. I made that mistake. I'd be lying if I said that I did it on purpose just to test you. But it's good if I accidentally make these mistakes, then correct them. So hopefully, keeps you focused on what you're watching for. When you do this, I'd rather get them right perfectly. But if I do make a mistake, no harm done. So we can put this formula in the calculator. This one where you have to subtract the payment amount. Let's go back up where it first talks about annuities due, where you have to add 1 to the exponent and then you remove the payment at the end. So, actually, this is the other formula. Oh, yeah, that we did not use. Okay, this is good. I showed it, but we didn't use it. Right here. This one. That's good. So it's going to be future value was 15,000 times the interest rate 4 point, whatever that was, the number I messed up, 4.1 quarterly. So it's 0.041 divided by 4. In the bottom, we're going to have 1 plus 0.041. Make that a fraction. And then our exponent is you have to add 1 to it. So it was 44 payments, 11 times 4. It's n plus 1, so we make that 45. Oh, come down here. And then I believe it's minus 1 minus I. Yes. Divided by 4. We got it. 268.75. Okay, so I'm glad we got to use that formula. So let's see what else looks interesting here. Another annuity due. Okay, present value. Let's try that out. Ordinary annuity. So I'll do calculator first again. So the deposits are $22,656. I'm going to put the negative there. Now I'm going to zero, because now we're solving for present value, so I'm going to zero out the future value. You don't want to leave a number there. All right, let's check everything else out. Oh, it's an ordinary here, so that's going to be back to end right there. I don't know what the compounding period is. Quarterly, so that's still PY, CY are still 4. I'm going to be solving for the future value. Let's check the top here. 8 years quarterly. 8 times 4 would be 32. And it's 7.6%. And everything else should be okay. Oh, let me highlight PV. Alpha solve. So hopefully it's 539,507.40. Excellent. So we can pop this in the calculator real quick. So the present value formula of an ordinary annuity. Okay, we're using that formula because we were solving for the present value and not the payment. So it's going to be the present value, and the payment was 222, whatever it was, 22656. Start me a fraction up right here. And that's going to be 1 minus 1 plus, was it 7.6? 7.6 quarterly. Divided by 4. Oh, I see a mistake. That's got to be, I've accidentally hit times back over here. It's supposed to be a minus right there. There we go. And this is raised to the negative exponent. and it was quarterly for 8 years, so it's negative 32. And then the interest rate on the bottom, 0.076 divided by 4. There it is, 539,507.40. So you can pretty much do these however you want. A couple more left. I'm going to just see if any of them stands out. This one's a payment, so it's just solving for the payment. Let me see what 9 looks like. Okay. This one's a future value. Tell you what I'll do just to make it quicker. I'll do both of these problems with the TVM solver instead of typing the formula in. So this is an ordinary annuity, so it's going to be present value, so we're looking for the payment. 93822. So you see this one is just basically the opposite in the sense that we are finding the payment now. Well, let's get everything else in there. 4.4% compounded monthly, 15 years. 15 times 12, it would be 180 compounding periods. 4.4. So with PV, okay, monthly, so I got to change that to 12. So we're still at the end, payments at the end still, so we're good there. Future value 0, that's good. Let's get our payment right here. Alpha solve. About 712.95. Look at us go. So I'll do this one real quick. So this one's a future value. They're saving up to have a certain amount or whatever. Well, not a specific amount. That's if you were trying to get a specific amount, you would be solving for the payments. So here they're just depositing this weird amount, and they're going to see how much they have in the account after 6 years. So they're $503 per month. So it's going to be like a sinking fund. Future value, because you're trying to get to the money in the future. So, okay, let's do this. 6 years, monthly, that'll be 72. So I can just start right from here. %. PV, let's zero that out of there. I don't want that. And let me double check this, but I believe the payment was 503. And we're looking for the future value. And it'll be end again because it's not an annuity due. Oh, let me double check. 503. End payments end of each period, so 12 times a year. Let's go highlight the future value right here. Alpha. 3962603. Oh, they almost got me. Look at that. I told you that's what. Okay, that's why I thought some of them might say round to the nearest dollar. So, okay, I was going to put the 2 decimals in there, but I'm sure it wouldn't have liked it. Well, let's see if this is right though. Okay, sneaky. But that's the good news about an exam. That's not going to be a problem. You're going to see all the answers. They're going to be either, probably all have decimals, like dollars and cents. But there's no way you're going to have a question where it was 3962603 and then 39626 and then try to trick you on the rounding or anything like that. They do a good job of tricking you here, but so, all right. Excellent. So I believe that's going to conclude this video on annuities, future values, and sinking funds.